let's take a look for a moment at something called similar figures. So the idea here is to understand what it means for figures to be similar and where this idea comes from. So let's start with a definition. Two figures are going to be similar if they have the same shape but different sizes. So again, we're looking at two things that look on the surface exactly the same, but they are just different sizes. And here's a nice little example of that. We've got two sets of figures here, and these figures are going to be congruent. They're the same shape and the same size, 5 for 5, 4 for 4, 3 for 3, etc. So these two right here are what we call congruent. That's a topic we're familiar with. These two are going to be similar. So they have the same shape but different sizes. And so we have our terms for that, congruent and similar, and symbols. So recall that congruent meant they're the same shape and the same size, and the symbol reflects that. The tilde over the top represents the same shape, and the equal sign underneath represents the same size. Well, with similar, they're not the same size, so we just keep this. So this would be the symbol for similar figures. So let's talk about how you can create similar figures, because it has a lot to do with dilation. Remember, congruent figures were figures where we could take any combination of the isometries, translations, reflections, or rotations, and move them around to lay them right on top of each other. With similar figures, we can see there's no combination of isometries in the world that's going to make that fit perfectly on top of that. We can get them in the same place, but because they're different sizes, they're not going to match up point for point like congruent figures would. Similar figures can be laid over top of each other with some combination of isometries and a dilation. Another way of looking at this is that similar figures are the result of taking a dilation of one figure on top of the other. So for instance, if we take this triangle, the smaller one, and we dilate it with a scale factor of 2, every side is going to be twice as big as it used to. So 5 would become 10, 4 becomes 8, 3 becomes 6. So the connection between similarity and dilation is that similar figures can be created by dilating one of the figures. So if we dilate this figure, we can turn it into this, or the other way around if we invert our scale factor. Alright, so another thing that we need to look at is that they have proportional sides, and that has to do with the dilation thing that we were just talking about. A proportion means if we set something up there, it's equal fractions. And essentially it's this. There is some number, the scale factor of the dilation, that I can multiply all these lengths by to turn them into these lengths. Same thing here. There is some number I can multiply 10 by, 1/2, to give me that side, and if I use that again, I'll be able to produce all the other sides from it. In this situation, we say they have proportional sides if there's one number that you can multiply all the sides by to get all the sides in the similar figure. Alright, just as with congruence, we can also talk about ways to prove triangles similar. So remember, similar means they have the same shape but different sizes, and so here's the shortcuts we can use to determine that they have the same shape but different sizes. And the first is angle-angle. So if I have any two set of congruent angles on two different triangles, I can automatically say that those triangles are similar. So if I have two sets of corresponding congruent angles, the triangles are automatically similar. The other one is SSS, and notice this is exactly like the same. We had an SSS for congruence as well. The SSS for congruence said we had to have three sides congruent. Notice that for similarity, though, we need three sets of proportional sides. That is, sides where one number multiplied by all the sides on one triangle will give you all the sides on the other. So if all three sets of sides are proportional, then we have similar triangles. And finally, we have a side-angle-side theorem for similarity as well. And what this says is it's just like side-angle-side for congruence, except instead of the two sides being congruent, the two sides must be proportional. So if we have two sets of proportional side and the included angle, the angle that's squished in between them, if those are congruent on the two figures, then they're going to be similar. And we'll look at some example problems of this a little bit later on. But again, these are our three methods of proving triangles similar. Remember, similar means they have the same shape but different sizes. And similar figures can be laid directly over top of each other through a dilation and some combination of the isometries.